All right, guys, here we go. Y'all ready? So, a lot of this, a lot of these ideas, you guys already kind of know. And sorry that it says review from yesterday. That's because when I wrote these notes out, these are actually from last year. But when I typed out one little sentence, we were going to continue from the notes. 18. No big deal. So check it out. It says example one. For each of the following functions, use the first derivative test to find the local extreme values. Identify any absolute extrema. Okay, first derivative test, we actually already used it. We just didn't call it that. What the first derivative test is, if the derivative changes from positive to negative, you have a max, right? If the derivative changes from negative to positive, you have a min. That is first derivative test. What's up, guys? Yeah, go for it. They're in the back. All right, so here we go. You see this function here? I'm going to find critical values, critical points. How do we do that? We take a derivative and we'll equal it either to 0 or undefined. Since it's a polynomial, it's going to be equal to 0, right? So f prime of x equals 3x squared minus 12. Does everyone know why I did that? Okay, I'm going to factor out a 3, and I'm going to be left with x squared minus 4. And if you want, you can do difference of squares. 3x minus 2, x plus 2. You don't have to. We're equaling that to 0. So my two critical points are 2 and negative 2. Are we okay with that? Then I'm going to do a number line. Call that number line f prime. Negative 2, 2. I'm going to plug in values into the derivative, not the original, into the derivative. All you care about is the sign. You do not care about the actual value. Right, Gomez? All right. Because we want to know if the original is increasing or decreasing. If the derivative is positive, f is increasing. If the derivative is negative, f is decreasing. I'm looking for maxes and mins, and here's how we're going to find it. You know what I mean? All right, so here we go. Negative 10. If I plug in negative 10, negative times a negative is a positive. I plug in a 0. Negative times a positive is a negative. And I plug in a 10. Positive times a positive is a positive. Do I have a rough sketch of how this graph probably looks? Yeah, probably something like this. Let's see. Increasing, decreasing, increasing. So probably looks something like that. At negative 2, that is a what? It's a critical point, but what type of critical point is it? Max, min, or neither? Max. What about at 2? Min. Are these absolute or just local? Just local because it goes up forever and it goes down forever. So I'm going to write x equals negative 2 is local max, and x equals 2 is local min. No absolutes. How do we feel? Negative 10. Yeah, I could have put negative 3, but I just like to go like way out there. Then I put in 0. I read it left to right, so I put in 0. And then I put in 10. All right, let's do the next one, guys, g of x. So I'm going to do product rule. There was no way around it. You have to do product rule, guys. First, times rid of the second, plus second, times rid of the first. And I know some of you guys do it the other way around. That's fine. I'm going to factor out an e to the x. X squared minus 3 plus 2x. And And this looks like, and that looks like it's factorable. Equal that to 0. E to the x will never be 0, but I have some factors. E to the x. Never touches. It has a limit of 0 if x approaches negative infinity, but e to the x will never equal 0. It's the domain. The range is all values larger than 0. This one here, guys, is going to be x plus 3, x minus 1. I think we're okay. And then we just find our x values, right? X equals negative 3, x equals 1. Those are critical points. Those are candidates for max and mins. They're not always max and mins. Are we still okay? Yeah. Here we go. I draw a number line. I label this f prime. I go negative 3, and I go 1. We still all right? Oh, g prime. You're right, miss. Let's be consistent. We don't have to worry about e to the x. Chavez, why not? E to the x looks like this. E to the x is always above the x-axis. So e to the x is always positive. And relax if you feel like, man, I need to go over that. It's probably because we've been in a pandemic a long time, and in Algebra 2, it's fine. Are we okay right now, guys? All right. What are we going to do? So I'm going to plug in numbers. I don't care about e to the x. I'm just going to plug in numbers into what I have left. Negative 10. Negative 10 plus 3 is a negative. Negative 10 minus 1 is a negative. Negative times a negative is a positive, or plus. No yawning. The next one's a demerit. If I plug in a 0, and I'm kidding, YouTube. I'm not going to give demerits out for a yawn. I'm plugging it in right here into this equation. If I plug in a 0, 0 plus 3 is 3. 0 minus 1 is a negative. Positive times a negative? Negative. If I plug in a 2 or a 10, positive times a positive? Positive. So at x equals negative 3, what do I have? A max, and at 1 I have a min. So let's write that down somewhere. Right here. X equals 3 is a max, comma, x equals negative 3, sorry. X equals 1 is a min. And they're both local, not absolute, because I see this going down forever and going up forever. Just like letter A. When I have something like plus minus minus, or minus minus plus, or minus plus, like let's say I just have plus minus, and that's it, that's all I have, then I know that has to be an absolute max, because my function increases left to right, hits that critical point, and then goes down forever. You know what I mean? It's the only critical point where something's happening, like an x squared or something like that. How do we feel? Yes, so this is fair game. I'm not going to ask like, oh, use first derivative test where you have to do this, but there will be a question. At the moment, there's only one. There will be a question that says, tell me where this function is increasing. And you have to figure out where the derivative is positive. Or I can tell you the other way. Tell me where the function is decreasing. And you got to tell me where the derivative is negative. Cool? Cool? Okay. All right. Are you guys ready to talk about concavity? Draw a sinusoid. This is concave down. This is concave up. There's a point of inflection, right smack in the middle, And that is called an inflection point. Using context clues, an inflection point is where the concavity changes. Sorry. No, you're good, you're good. Are we okay, guys? Okay. All right, so I think that's all you got to know. Well, there's more to it than that. Let me see. Do I give you more details here? Yeah. Okay, but do we know at least that? And that's from like algebra, right? Algebra 2. Okay. So that's what an inflection point is. So let's observe what happens. Let's see. Let's observe the behavior of f prime when f is concave up. So I'm going to draw a strictly concave up function. So here is a concave up function. We're going to call this f. You guys ready? I want you to tell me what is happening to f prime. So check it out. F prime at that moment is some negative value. I don't know. Assign it a negative value like negative 10. You guys see that? I'm going to move a little more forward, left to right. And I notice that I still have a negative value there, but it's not as steep. So it's like a negative 5. Do you guys see that? Then as I get closer to this location, I notice that f prime there is 0. Then I notice right here that f prime is like 1 or 2 or 4. And I notice that f prime there is like 5 or 10. So left to right, what is happening to f prime? Okay, well, be careful. So let me give you some numbers. Negative 10, negative 5, 0, 4, 8, 10. What's happening to those numbers? I'm increasing. Do we notice that? Yeah. So if f is concave up, f concave up means f prime is increasing. Do you guys agree? Just by looking at that? Okay. You guys ready for this next step? If f prime is increasing, what does that mean about f prime prime? I don't know. Okay. Let me say something different. Didn't you just tell me right here that if f, let's look at letter A. We said that f was increasing when f prime was positive. Didn't you guys tell me that? Okay, so if I have a statement like f prime is increasing, what does that mean about f prime prime? That it's what? Yeah. That's it. I don't want you to be a robot. You can be a robot very easily. Yes, I'm going to explain. If f prime prime is positive, that means f prime is increasing. If f prime is increasing, that means you're going to be creating this type of shape because your slopes are getting bigger and bigger. So the rate of change is increasing. Does that make sense? Or does that not make sense?
So f prime. So if that is f,
Uh-huh.
f prime is like that red line.
No, it could be if the graph of f looks like that, f prime will just be increasing.
Oh, okay. So it's increasing.
F prime is.
Okay.
And f prime prime will just be positive. It's above the x-axis. F prime prime.
Okay.
Yeah, I know it's a lot to take in initially, but it makes sense because we still follow the rules. So let's talk. Don't worry, this is the first time ever. If f prime is positive, doesn't f increase? Yeah, because remember f prime means slope. So if f prime prime is positive, oh, what does that mean? The rate of change of your slopes. So if your rate of change of your slopes are positive, that means your slopes are getting steeper and steeper. And that's going to create that concave up deal. Does that make sense to you?
A little bit, yeah.
What's up, Arispe?
So would all the like F prime that becomes like F prime prime, F prime prime, that would be positive.
The only thing I know for a fact is that F prime prime is positive and that F prime is increasing. I do not know if F prime is below the x-axis or above the x-axis, but I know that F prime, well, actually we do. We do. Okay, should I just put a grid on it? All right, here's my grid. This is my first quadrant. Don't write this down, just listen. You see this in green? Those two in green? F prime at those two locations where I'm in green, F prime is negative there. Why do I know that F prime is negative? Well, look, it's easy to see. You can see it's a negative slope. You can also see that F is decreasing. Do you guys agree? But F prime prime is positive. The rate of change of the rate is positive. Chavez, I don't understand that. There's too many play on words. Think of this like negative 10. Think of this like negative 5. The only way to go from negative 10 to negative 5 is if you add 5. Does that make sense? So the rate of change of the rate is positive. It's getting less, and the number is getting bigger. F prime prime, right? Okay, so all I can tell you is that F prime prime at these locations, what I just circled, is positive because F prime is increasing. Do you guys see that? I know it's hard. It's really hard, especially in the beginning, but it gets easier the more we're about to do that right now. So check it out. I'm going to draw concave down, something that's specifically concave down, like a parabola. I'm going to call that F. Are we okay? So check it out. I'm going to draw some dots. There's my tangent line. It's like pretty steep, like 12 or something, you know. Another tangent line, that's like 6 or 5. Another one, that's like 0. Another one, that's like, I don't know, 2 or 3, 4, negative 2, negative 3, negative 4, negative 11. What's happening? F prime is decreasing, which means F prime prime is negative. Good job, guys. So F prime is decreasing. Because F prime is decreasing, this concludes that F prime prime is negative. Good job. All right. You guys ready? Listen to this very carefully. Yes.
So F prime decreasing and F prime increasing makes sense to me. I think it's the F prime prime positive and negative twice.
Okay. Do you agree that if F prime is positive, F is increasing? It's the same deal with if F prime prime is positive, F prime is increasing.
Oh.
Do you see that? Like they're connected. It's just a derivative away. So F increasing, F prime positive. All right, now let's talk about the difference between F prime and F prime prime. F prime increasing, F prime prime positive. Do you see that? All right, guys, real quick. This is super important right here. If you're gonna learn one thing and one thing only, this is the thing. Can you be a robot and do this? Yes. I don't want you to, but yes. The only thing you gotta know, if F prime prime is negative, your F is concave down. If F prime prime is positive, your F is concave up. Can you be a robot and do that? Yeah. But I want you to understand why. So why? What is the why? What's the reason? I feel like Cardi B. What is the reason? Okay. All right. Let me tell you the reason. If F prime prime is positive, that means F prime is increasing. If F prime is increasing, That means your tangent slopes are getting bigger and bigger, and that's what creates that concave up deal. Does that make sense? All right, so if f prime prime is negative, that means f prime is decreasing. And if f prime is decreasing, remember what that means. That means your slopes are getting smaller and smaller. By smaller, I mean more negative, right? So that means that it creates that concave down deal. 10, 8, 7, 6, 5. See, it makes that concave down. Does that make sense to you guys? Okay, there's only 4 types of graphs. Only 4 types of graph. And maybe I'll put them in here. Oh, look, okay, let's do the conjecture. So here we go. The conjecture, here's what all we have to know. This is the most important part. If f prime prime is positive, this means 2 things. What are my 2 things? In terms of f prime, that means that f prime is increasing. And that means also that f is concave up. Perfect. If f prime prime is negative, this means 2 things. That f prime is decreasing, and that f is perfect. There really is only 4 types of graphs. There's only 4 types of graphs, so don't make it harder. Either f is increasing concave up, f is increasing concave down. So how does that look like? Left to right. F increasing concave up, f increasing concave down. Do you see both of them? That's increasing, and then the other one is f decreasing concave up, f decreasing concave down. Those are the only type of 4 graphs there are. Does that make sense to you guys? So in this case, let me tell you on this case. So on this case here, f prime is positive. Chavez, how do you know f prime is positive? Because f, we're calling this f. F. In this case, f prime is positive because they're increasing. But on this one here specifically, this is concave up. So this one, f prime prime is positive. And I'll try to color code. On this one again, f prime is positive, but f prime prime is negative. Yes. So yeah, you're right. Your tangent slopes are decreasing. F prime is decreasing, even though f prime is positive, but it's decreasing. That makes sense? Yeah, I know it's hard, but it's gonna get easier once. Oh yeah, because there's a lot of things going on. That's why. There's a lot of things going on, but your brain, with experience, will figure this out and slow it down. On this one here, on both of these situations, f prime is negative. Chavez, how do you know f prime is negative? Left to right, is this graph going down? Yes. But this one right here, this one's concave up. So if it's concave up, that means the second derivative is positive. And you can kind of see, even though f prime is negative, notice that negative 10, negative 8, negative 5. Yeah, I can see that my f prime is increasing, which means f prime prime is positive. And on this one, it's getting more and more negative, so this one's concave down, so this one's f prime is negative. Ask. I hope I didn't say the wrong word.
So the slope of
Negative 10, negative 8, negative 5. So that looks like it's f prime is increasing. Even though f prime is negative but increasing here. So that's why f prime is
what
positive.
is it f prime decreasing because it's going from 10 to 8 to 5?
No, look what you just said.
F prime is decreasing.
F prime, no, f is negative. F prime is negative. But f prime, you're going from negative 10 to negative 8 to negative 5. Not 10, 8, 5. Negative 10, negative 5, negative 2. You're on the number line, the more right you go, that means you're turning more positive. Negative 10, negative 8, negative 5.
So increasing and decreasing refers to the sign. Yeah.
Increasing or decreasing refers to, on a number line, which way am I moving?
Right.
If I'm moving right, you're increasing.
But then the f itself, when we say
Oh, this F itself is decreasing.
Right. But F prime is increasing.
Yes, F prime is increasing. Why?
Because when you gave us the numbers,
You could also say because you're concave up. The only way you can be concave up is if F prime is increasing. Does that make sense? Negative 10, negative 8, negative 5.
So the rate of change of the slope.
The rate of change of the slopes. Your slopes are increasing. The rate of change of the slopes are positive. If you know what I mean? You correlate the word F prime with slopes, so the slopes are increasing.
So the slopes are increasing.
So the rate of change of the slopes are positive.
But the slopes, well, isn't the slope decreasing?
No.
I think it's like, it looks like.
The slopes are negative.
So the slopes are negative. The slopes are increasing, right?
The slopes are increasing.
Negative.
Less negative. Negative 10, negative 8, negative 5, 0. They're getting less negative. They're moving.
Yeah, that slopes are smaller.
Oh, okay. Be careful with physics.
Yeah, exactly. I think I'm getting it.
Yeah. We're just at a number line, the more left, negative 1,000
But the
is
actual
considered.
number, like it doesn't matter because it's negative
Okay, say it again.
like the actual number, that's not what we're talking about. We're talking about getting close to negative.
That's negative. Yeah, because negative 10 and divide 4, 3. Don't worry, we're gonna put it all together in a little bit. You guys ready? There is something called a concavity test. Don't worry, guys. We're not gonna go full out right now. There's something called a concavity test. Sometimes you gotta use the concavity test to test for maximum or minimums. Actually, you don't need the concavity test for this too. Okay, it doesn't matter. I guess we're not there yet. I chose this question on purpose. Y equals x squared. That is always concave up, no matter what, right? So that means my second derivative better be positive. That's all I care about. So it says use the concavity test to determine the concavity of the given function on the given intervals. So what's the concavity between 3 and 10? Well, I already know it's concave up. Let's see if it's true. Y prime equals 2x. Okay, let's take another derivative. Y prime prime equals 2. Is it always positive? Hence, comma, y equals x squared is always concave up on every interval. So maybe next time I'll just delete the 310. Cool or not cool? Look at this one. 3 plus sine x. Hopefully you guys know that sine x goes between concave up and concave down many times, right? And all that 3 does is just move sine x up 3 times. Okay, so I want to know where I'm concave up and concave down. And we know this if we were just to plot y equals sine x. But let's do it with our second derivative test, concavity test. So I'm going to take a derivative. What's the derivative of sine x? I'm going to take another derivative, y prime prime. What's the derivative of cosine x? I'm going to equal that to 0 to find, now by definition, I got to tell you this, by definition, setting the second derivative equal to 0, that is not considered a critical point. We actually had a discussion with a professor about this. I think he was being too picky, but whatever. Because I used to call it a critical point, and the professor goes, y prime equaling 0 or undefined is a critical point. So then I'm like, okay, but something's happening here, so why can't I call it a critical point? And like, oh, call it a candidate. So fine. So this is a candidate for concavity, a point that is possible candidate for concavities. Does that make sense? Because we're, for a point of inflection, a candidate for a point of inflection. Sorry if I'm talking too fast. What's the point of inflection? Where the concavity changes from from concave up to concave down or vice versa. Does that make sense to you guys? So these are just candidates for points of inflection. So can you guys tell me where sine x is 0 from your pre-cal days?
0,
0, pi, and 2 pi. 0 and 2 pi I don't have to worry about because look at the interval. It's between 0 and 2 pi. So I'm going to write y prime prime. I'm going to close it off, 0 and 2 pi. And I'm going to put pi. So any number, now I'm Chavez, where are you plugging it into? I'm plugging it into sine. Any number between 0 and pi for sine is positive, right? Because that's quadrant 1, quadrant 2, the sine y value. But I have a what in the front here? A negative. So that means anything between 0 and pi will be negative for the second derivative. And any number between pi and 2 pi, that's quadrant 3 and 4, will be positive because of the negative in the front. Are we okay? So, y equals 3 plus sine x is concave down from 0 to pi and concave up from pi to 2 pi. And we know that because we know how sine x looks like. I know this is 3 plus sine x, but I'm going to go ahead and just draw sine x for you guys. This was pi, this was 0. This was pi. This was 2 pi. And look at that. Is it concave down between 0 and pi? Yeah. Is it concave up between pi and 2 pi? Yes. What do you guys think? Don't worry, we're about to put it all together. Oh, look at this one. Okay. This is the, okay, don't worry guys. Can we take some more or no? It's not 10:45 yet, right? Are we still okay? All right. Just by looking at this picture here, how do you spell? You all right? Okay. Can you tell where it's concave up and concave down? Yeah, it looks like it changes, bam, right there, concave up, and then bam, right there. Do you guys see how that worked out right there? That graph is this one right here. The question here is find all points of inflection. You're going to need a calculator. Do you guys have your calculator? Every time you get a chance to use your calculator, let's use it. Were you guys able to get a key? I'm pretty sure it is. Which one's missing? 14? Okay. That's fine. No, we're not bullies. Okay. All right, we're going to teach you how to use the derivative on the calculator for the first time. Have we used it before? We've never used it? Okay. So here's my equation. I want to find the points of inflection. So if I want to find the points of inflection, I need to take the derivative twice and equal it to 0 to see what my candidates are for points of inflection. In this case, you already can see that it's going to be whatever the second derivative equals 0. Cool or not cool? So here we go. First derivative. What's the derivative of e to the negative x squared? Itself times. Perfect. Now I need to take another derivative, y prime prime. How do I take the product rule? First, negative 2x times the derivative of the second. We already know what the derivative of e to the negative x squared is. We did it a little while ago. Negative 2x e to the negative x squared plus second e to the negative x squared times the derivative of the first, negative 2. Are we okay? Okay. I would leave it like this. I would not bother simplifying. I'm going to use the graphing feature of my calculator. So I go to y equals, and I'm going to type that in. Can you guys hook me up with what I have in there? Parenthesis, negative, what was it? Negative 2x, close. To the negative x squared, right? No, you're good, miss. Was it like that? and then a plus, and I already forgot. E to the negative x squared, negative 2. E to the negative x squared, and then close this one times negative 2, right? Okay. I hope I did it correct. Hopefully we're going to get the same digit as in a little bit, but you'll see. You guys okay? All right. Don't push graph yet. I can see that what my number is supposed to be. I see 0.707. So I'm going to look. Remember, I just want to see where it crosses the x-axis because this is my second derivative. So wherever it's turning negative to positive or vice versa. So I click on window. I'm going to go -1 to 1. And I want to hover close to the x-axis. So usually I go -1 to 1. And then I push graph. Yeah. I used a square window, -1 to 1, -1 to 1. Chavez, why? Because I want to know where the second derivative crosses the x-axis. Does that make sense? Notice this. What am I looking at right here? I am looking at my second derivative graph. So I am concave up. Chavez, how do you know you're concave up? The original. The original is concave up until I hit the 0. And then I'm concave down forever until I hit the next 0. And then I'm concave up for a little bit. Do you guys see that? Between -1 and 1. I just push graph. So here we go. What is my point of inflection? Second, calculate. Number 2. And it said left bound. I'm just gonna go. I'm looking for my left one first. Come on, buddy. There you are. Enter. Right bound. Enter. Guess. Nope. -0.707. Oh, I'm gonna do it again. It tells you. Okay, so what? Check it out. Second, calculate number 2. Initially, well, now I have it here, but it tells you where it starts at, like where it's at. So now I know it's over there. I want to find the other one. So I'm going to go left bound, go. You can also type in a number. There I am, left bound there. Right bound, I'm going to go past it. Right there is good enough. Guess, nah, 0.707. It's symmetric because it's an even function. I just pushed enter to look between the left and the right. Left bound to the left, right bound to the right. Cool or not cool? Did you put that? Yes. Did you put that? Yeah. Did you put that graph? Do you have a plot on? You see on the top, my plots are off. Plot 1, plot 2, plot 3. Maybe you're not using a negative. Maybe you're using a minus. I'll go over there right now, miss. Don't mess with the resolution. Don't mess with the delta x. Okay. Let's see. Maybe it's easier this way, guys. So we know what the answer is. Point of inflection. Plus minus 0.70710678. That's what we got. Or really, it's not really a point because the point is x, y. So I probably should point of inflection at x equals, or that's fine. Say it again. Yes. Because the second derivative will give me possible candidates for points for where the concavity changes. A concavity has to change from negative to positive or positive to negative for it to be a point of inflection. Because if it's positive, you're concave up. If it's negative, you're concave down. All right, let me teach you how to do a derivative really fast on your calculator. I don't know if I'm going to regret this, but I'm going to go ahead and teach you. You guys ready? Okay, math. You know what? Here's how I would do it. What was the equation? 2 or e to the negative x squared. Okay. Here's how I would do it, guys. On y2, I'm going to type in e to the negative x squared. So remember that it's on y2. And then I would go, how do I get my screen to be like this? I just go second quit. I go math. And then I look for numeric derivative number 8. And then I put ddx of y2, alpha trace y2. And, well, that's how you get the first derivative. I don't want the first derivative. Actually, that's not going to work. The way we did it is going to work because we don't have an x value. That's what we're looking for. This is dumb. This was dumb. Sorry, guys. Sorry for telling you that. All right, what's up? What was the question? Okay. Yeah, you don't need to worry about it, but, or at least for now. Number 8 will tell you the, I guess I'll show you how it works. Okay, let me quit this. I'm messing it all up. All right, let's take a quick break. You guys ready? What's the derivative of x squared? 2x. What's the derivative of x squared at x equals 3? What's the derivative of x squared at x equals 3? 6. Here's how you use it. Math, numeric derivative number 8. I type in x squared. Oh, that's an x. X. And I guess I'm going to have to delete the, oh, there it is. And I put in x equals 3, and then we better get 6, right? And there it is. Have you used that before or no? That's how you get a derivative at any value that you want. In this case, it wouldn't have worked because we're looking for an x value. So we have to go the graphing route. What's up, Taylor?
I think I get it. Yeah. It's a lot.
All right. Let's do one more. And then we'll stop right here at this one. I think once we do this, you're going to get it a lot better. Okay. This is the last example we'll do for today, guys. So it says, you guys ready? The graph of the derivative of a function f on the interval -4 to 4, so it's a closed interval, is shown to the right. Answer the following questions about f, justifying each answer with information obtained from the graph of f prime. Before you start anything, this graph right here that I'm looking at is what? F prime, label it. So are you looking at f? No, you're looking at f prime. Letter A, on what intervals is f increasing? When f prime is positive, where is f prime positive? Perfect. F is increasing on interval -4 to 1, since f prime is positive on this specific interval. It's above the x-axis. Does that make sense to you? Okay. If you wanted to cut it in pieces, f prime is positive from -4 to -2, and then again from -2 to 1, you may, but it's still correct. It is the best answer. Are we still okay, guys? All right. On what intervals is the graph of f concave up? No.
When f5 is increasing.
Perfect. Where is f prime increasing? There's two intervals. -2 No.
2 to 0.
2 to 0.
-2 to 0, and then 3 to 4.
3 to 4. Perfect. F is concave up when F prime is increasing. Period. This occurs specifically on intervals -2, comma to 0. Use parentheses for concavity, and 3 to 4. That's it. So that's where F is concave up. Because concavity and the rule of thumb is, if you were to use brackets, that's still kind of right. But the rule of thumb is you increase and decrease on an interval, and then when it comes to concavity, right at -2, that's the point of inflection. It doesn't have like a concave up, concave down. Does that kind of make sense? Yeah. So the rule of thumb is for increasing, decreasing bracket, concavity, parentheses. At which x coordinate does F have a local extrema? That means where do I have local max, local min? Okay, good job. Am I including endpoints? I want to say yes. So I'm going to put include endpoints. On the AP exam, they will probably have open. They'll probably have -4 to 4 parentheses, and that means you don't include the endpoints because they probably want to avoid ambiguity. I want to say include the endpoints. So at -4, at x equals -4, does F have a local min, local max, or neither? Think about it for a little bit.
So it's decreasing. So F will be decreasing.
F is, okay, this is F prime. At -4, is F prime positive or negative? Positive. So at negative, so think about it, visualize it in your head. At -4, and then you just start increasing immediately.
Okay,
So
so there's a critical point at 1.
oh, there's a critical point at -2 and at 1, yes. But the -2, 1 is nothing. All right, so -4 is a local min. Does everyone know why? Because the derivative is positive, so immediately you start increasing. Then at 1, what is 1? Max or min?
It's going from positive to negative, so it's
Perfect. Local max. And then at 4, max or min?
if we assume it continues upward, then
Well, it's negative between 1 and 4, so you're going to keep going down, 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 down. And then right at 4, you have a horizontal tangent. Min. We don't know enough yet about absolute, because we got to look at area under the curves. And at -2, it's neither, because I'm going up, I have a horizontal tangent for a moment, and then I go up again. Because F prime is positive. F prime is positive means F increases. What are the x coordinates of all inflection points for the graph of F? So I have inflection points where F prime prime changes signs. So that means where F prime changes from what to what? No, that's F prime prime. Where F prime prime changes from positive to negative, that changes signs. But I don't have F prime prime, I have F prime. Where F prime changes from increasing to decreasing or vice versa. Does that make sense, guys? Okay, I'm going to repeat it just in case. If F prime is increasing, F prime prime is positive. If F prime is decreasing, F prime prime is negative. Does that make sense? Hey, there's another yawn, that's a demerit. All right, here we go. What are max coordinates for points of inflection, guys? One of them happens at -2. The next one happens at 0. The next one happens at 3. this is where f prime changes from, which one's the first one? Decrease to increasing? From decreasing to increasing, and vice versa. Make sure to put the vice versa. Does that make sense? Okay. Maybe there's a way to say it better, but this is full credit right there. Okay, here comes the moment of truth. It does not have to be perfect, guys. Sketch a possible graph of f. If you try to do it all at one time, it's going to be hard. Remember, there's only 4 types of graph. Either f is increasing concave up or increasing concave down, or on f is decreasing concave up, decreasing concave down. Cool? Let's do it in sections. And I'm going to try to color code it. So this is f prime. I'm going to start it with red. So this part in red, f is increasing, but is f concave up or concave down? F. F is increasing and concave. Okay, let's slow down. What's going on with f prime here? Is f prime increasing or decreasing? F prime is decreasing. So remember, if f prime is decreasing, that means f prime prime is negative. So that if f prime prime is negative, that means f is concave down. So that part in red, f is increasing and concave down. Perfect. So start with an increasing concave down graph. Increasing concave down. And right at -2, you should have a horizontal tangent. So I'm going to say right there is good enough for that piece. I should have started it lower. That's fine. Okay, I'm going to color code it. Now, f, look, this in blue. Is f increasing? Yes. What's the concavity of f at that moment in blue? Concave up. Increasing, concave up for a little bit. So increasing, concave up for a little bit. There it is. And then let me change the color to green now. What about this part here in green? From 0 to 1. F is increasing, concave. F prime is decreasing, which means concave down. So F is increasing, concave down. For a little bit. At 1, you have a horizontal tangent. So what was it? Increasing, concave down. Increasing, concave down. Bam. All right. And now let me change the color again. Let's put it to black. All the way to 3. So from 1 to 3, F is decreasing because F prime is negative. And F prime is decreasing, so that means I'm also concave down. So decreasing, concave down. Decreasing, concave down. Oh, that's a good one right there. Decreasing, concave down. And then let's change it up, my color again, to red. And now look, F is still decreasing, but it's concave up. So decreasing, concave up. So it looks something like that. What do you guys think? No, yeah, you can. Well, it takes practice. We're going to do a whole bunch of practice. All right, let's stop right here. We have a little activity for you guys. Relax. It's going to be fun. All right, guys, you guys ready? All right, here we go. Don't worry, I'll give you guys some downtime. This is only going to take like 10, 15 minutes, and then this thing, now that you guys are warmed up, will only take maybe 30 minutes. But I think you guys will be pretty fast at that. All right, this is called the second derivative test for local extrema. Remember, extrema is the Latin word for extreme, so we're just looking for max and mins. And there was one year, I can't remember the year, maybe it was 2016, maybe it was 2015, I can't remember. There was one year in the free response question that they asked students like prove that it was a max or min, and they didn't ask like by what method. And there was so many that tried to do the first derivative test, but you could not do it with first derivative test. You had to do it with second derivative test. And I know right now you're like, well, I don't understand. Or maybe you're like, I don't know what you're talking about at all. But you'll see, it's not that bad. So this is called the second derivative test for local extrema, and they give you, and it's, I know we call it theorem 5. We're not using a textbook following theorem 1, theorem 2, theorem 3, so it doesn't matter. So how does this look? So it says, if f prime of c equals 0 and the second derivative is negative, then f has a local maximum at x equals c. All right, if you draw a visual, you're going to see that it's so obvious. If you want to be a robot, you can just memorize that. But if you do a visual, you're going to see that's an obvious thing. What does second derivative being negative mean in terms of the f? That f is...
No, it's concave down.
Yeah, that's all it means. Second derivative negative means that f is concave down. You can also say that f prime is decreasing, but that's not what I asked. I asked, what is it in terms of f? Does that make sense? All right, well look, this one says derivative is 0. What does that mean in terms of f? That I have a horizontal tangent. So if you draw a visual, oh, concave down, horizontal tangent at c, it looks obvious that that has to be a max. Look, do you guys see that point? Is that a max? Yeah, it's a max. Why is it a max? My derivative is 0 and I'm concave down. It must be a max. Cool or not cool? Yeah. So look at the other way around. Look at number 2. It says the derivative is 0 and second derivative is positive. If the second derivative is positive, what does that mean in terms of f? Concave up. So think about it. Concave up. And I have a critical point, or my f prime of c is 0, horizontal tangent. So that means this critical point must be a min. If you draw a visual, it's easy to see why. Does that make sense, guys? So anytime you get to this, just draw a visual. Like, oh, okay, what it means. Second derivative is negative, so that means f is concave down, and my critical point is 0, horizontal tangent. Boom. Cool or not cool? Cool. So let's see if we can use the second derivative test to figure out what these local extreme values are. So use the second derivative test to find the local extreme values of blah, blah, blah. So first, I'm going to take my first derivative. F of x equals 3x squared minus 12. And before I do my second derivative, I'm going to equal that to 0. And I'm going to find my critical numbers. Cool or not cool? What's up?
So your critical numbers you get them from the first derivative.
Yep.
Test.
Oh yeah, I'm going to use my critical numbers, and I'm going to plug this into the second derivative to see if I'm concave up or down at that point.
So your critical numbers are from the first derivative.
Yes, critical numbers is the definition is where the first derivative is 0 or undefined.
Okay.
Yeah.
Okay. So so even with the second derivative test, we don't do where the second derivative is.
No, where the second derivative is 0 is possible candidates for possible points of inflection where they change from concave up to concave down or vice versa. But I'm using the second derivative test to see if this is a max or a min. Does that make sense? So I guess let's go back real quick. I'm using the second derivative test to see if my critical numbers are max or mins. Cool? Okay. So I'm going to factor out 3 out, and I'm going to have x squared minus 4. And from there, I can say that x equals plus minus 2. Yeah, we did it earlier. Yeah. I think it might be the same expression. I can't remember. Are we still okay, guys? So these are critical numbers. F prime of negative 2 equals 0. F prime of 2 equals 0. Are we still okay? All right, I'm going to take my second derivative. F prime prime of x equals, what's the derivative of 3x squared? 6x. And I'm going to go f prime, sorry. There's 2 primes, it just looks like 1. Prime. F prime of negative 2 equals 6 times negative 2, which is negative 12, which is negative. So what does that tell you? And go slow. What does that tell you about negative 2 on F? So you're concave down. It's a max. Does that make sense? So I'm going to write F has a max at x equals negative 2 since f prime of negative 2 equals 0 and f prime of negative 2 is negative. And that is math language to say that f is concave down, and I have a horizontal tangent, hence that must be a max. Does that make sense to you guys? Perfect. I'm going to go ahead and test the other one. F prime prime at 2 equals 6 times 2, which is 12, which is definitely bigger than 0. So what does that tell you about x equals 2, f of 2? So your concave up, it's a local min. So I'm going to write since f has a min at x equals 2, since, and I probably should have used a different color, sorry guys, since f prime of 2 equals 0 and f prime prime of 2 is positive. And there it is, that's full credit. Now we just need a lot of experience. But do we feel okay with those two? Do we? Yeah. Do you see how we did it, guys? Yeah, see? Not that bad. We have some questions that you guys are going to answer. And don't worry, guys. Yeah. I wanted to see where the only time you have max and mins are at critical points. Well, and endpoints, but that's besides the point. The function's continuous for all real numbers. So if I have a max and min, it's going to happen at a critical point where the derivative is 0 or undefined. Why? Because at those critical points, when the derivative is 0, you have, like, your graph is either going to look, so how can it look? It can only look like this, or I guess it can stop like that, or it can go like that. Critical point there, critical point there, critical point there, critical point there. See, if it looks like that, that's a max. If it looks like this, it's a min. If it's like that right here, like that, that's neither. And that one's neither as well. It could also have been undefined if it was something like, see, that would have been a max. That would have been a min, where your derivative is undefined and stuff like that. Does that make sense or no? Okay. Thank you.
You're not.
No, I'm good. I didn't see that one right there, and I know that other teachers used to get Phoenix.
You're good.
I didn't realize.
Does that make sense, guys? Okay, are we cool? All right. Let's keep going, guys. So see if you guys can answer this question. Number 1, it says true or false. And we're going to justify our answer in a little bit. So it says true or false. If the second derivative is 0, then c f of c is a point of inflection. Think about it very carefully. What do you guys think? Does that sound like a good justification? It doesn't. So what's a better justification? False. Oh, you're close. If what is positive or negative?
It has to. F prime has to go from positive to negative.
Or
It has to change
the second derivative has to change signs in order for it to be a point of inflection.
It can't just be chilling at 0.
Correct, because that means if the second derivative goes from positive to positive, that means concave up. For a moment, I was like, oh, maybe I'll switch to concave down, and no, you continue to concave up. Does that make sense? So the best explanation is false. F prime prime must change signs at x equals c in order for x equals c to be considered a point of inflection. Does that make sense to you guys? Why do we always equal the second derivative to 0? Because that's a possible point of inflection. That's the only way you can change signs, if you cross the x-axis. Well, where the second derivative is 0, that's like how. Well, if the second derivative is 0, that means you have no concavity. So if the second derivative is always 0, it's like a linear line. If the second derivative is always 0, it's a linear line. Yeah, second derivative is 0 means no concavity. But it can happen where second derivative is 0 where you're changing concavity, right? Like if I go like that point right there is second derivative is 0. Right? Okay. Concave up to concave down. So where you change concavity is that moment. Now, what about this? Can you do this? Oh, that's a trick question. They're not going to do that to you on the AP exam. They did actually one year, but they went back and they were real soft on it. So don't worry about it. Yeah, I shouldn't have even brought it up. I was going to say there's no concavity. This is a linear line. So I have concave up here, and then I have no concavity to the right of that. So would that be considered a point of inflection? No, because there's no change in concavity. That's by the basic definition, a point of inflection is where you change concavity, concave up to concave down. So if you see something like this happening where you have concavity and then all of a sudden you have a linear line, that is not a point of inflection. They're not going to ask you that because that would be very, very mean. They did, but they learned from their mistakes and they're not going to ask that again. Cool or not cool? Okay, what's up?
Wait, just to make sure I understand.
Yeah.
When we say point of inflection, we're talking about graph of F, right?
On the graph of F.
But we use a second derivative to figure that out.
Yes, because the second derivative is what creates our concave up, concave down in terms of F, right?
So even on on F, if we're looking at the graph of the second derivative, if it changes signs, that's how we get it on the graph of F, the concavity changes.
Yes. If you're looking at a second derivative graph, if it's positive, F is concave up. If you're looking at a second derivative graph and it's negative, F is concave down.
Okay, so does that mean that we can look at the graph of F, saying, okay, well, the concavity changes here, so then this is also where the second derivative changes signs.
If it crosses the x-axis, yes. Yeah. Any questions, guys? Let's go to this one here, number 2. The derivative is 0, and the second derivative is negative. They're telling me that I have a max. Draw a visual and see what's up. Draw a visual for F. Well, this is concave down. No, there's no slope. It's a horizontal tangent.
Oh, okay.
Concave down, horizontal tangent. Is it a max? Yes. This is your second derivative test.
I thought that meant that the derivative was always 0, not just at C.
No, just at C. Yes. This is second dir test. If you see me write dir, it's because dir is code for Mathematica and Maple for derivative. Maybe even for MATLAB. We'll try it out one of these days. Or maybe they updated it with the newest edition. How do we feel, guys? All right, let's see if we can do number 3. Give it a 1-minute head start. You can do this without a calculator. Miss, I believe in you, miss. 523. Yeah, you can do it without a calculator. All right, here we go. If I want the points of inflection, I have to do how many derivatives? 2. Y prime equals 5x to the fourth minus 20x cubed plus 3. Did I do that derivative correctly? All right, I don't stop here. I go to the next one. So what's 5 times 4? 20x cubed minus what's 20 times 3? 60x squared, and then that's 0. Are we still okay? Yes. I don't need a calculator. I'm going to set this equal to 0 because if I do have a point of inflection, remember, what are we looking for? Where second derivative changes signs. If the second derivative changes signs, I have to cross the x-axis. Yes or no? Can we do this without a calculator? Yeah. Factor out a 20x squared, open parenthesis. You're going to have 1x minus 3, close it, equals 0. Are we still okay? Here are my candidates. X equals 0 is 1. What's the other one? X equals 3. Don't be so fast to circle 0 and 3. We got to check if the second derivative does in fact change signs. Are we all in agreement? So here we go. I draw a sign chart or railroad tracks or whatever you want to call it. Yeah, number line. Let me call it y prime prime. And I'm going to put 0 and 3. And I'm just choosing numbers to the left and to the right of that. So do I even have to worry about 20x squared? It's always going to be positive. So don't even worry about it. If I plug in a 0 into 0 minus 3, that's a negative. Do you see that? If I plug in a 1 into 1 minus 3, that's still a negative. And I plug in a number bigger than 3, like a 5, it turns into a positive. So how many points of inflection do I have?
1.
Just 1. Where at?
3 only.
3 only. Do you see how we did it? Yes, ma'am.
Why did you use
Because 20... Oh, the first derivative only tells me where f is increasing or decreasing. That has nothing to do with points of inflection. I have points of inflection where the second derivative changes signs. Right? If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. The first derivative only tells me if f is increasing or decreasing. That's all it tells me. Unless I have a graph of f prime, but I don't have a graph. If f prime is increasing, then yeah, I can say that f is concave up. Because if f prime is increasing, that means f prime prime is positive. Right? Do you see how it's all connected? No? Okay, do you know that the second derivative being positive means that f is concave up? Okay, so if the second derivative is positive, doesn't that mean that f prime is increasing? No. Okay, if f prime is positive, does it mean that f is increasing? Yeah, because those are positive slopes. Isn't the derivative between f and f prime just one derivative away? So isn't the difference between f prime and f prime prime just one derivative away? F prime prime. So if f prime prime is positive, that means that f prime is increasing. If f prime is increasing, it means that f prime prime is positive, right? Okay, if f prime is increasing, f is concave up. We can right? Are you sure? Okay, think about it for a little bit. What were you going to say, Ms. Guerra?
So what is the point into the, which equation did you plug into the line, the number line?
Oh, well, remember the question was, what's my point of inflection? So the only thing you care about is concavity. So you're going to be plugging in stuff into the second derivative because the second derivative tells you the concavity of f, or y equals. If the second derivative is positive, you're concave up. Second derivative is negative, you're concave down.
So true.
So you plugged it into the second derivative. It tells you the rate of change of your concave. It doesn't mean anything in terms of in terms of f. Doesn't mean anything. If you take enough derivatives, it's gonna flatline. You know what I mean? Any polynomial, you take enough derivatives, you're gonna flatline eventually. So 3 derivatives is all you need. It's just like with physics, position, velocity, acceleration. You take another derivative, it'll tell you the jerk, which is the rate of change of acceleration. But unless you have something that is like bouncing up and down really fast, like a piston, the more derivatives you take, it's going to zero out. You know what I mean? But if you have a rocket going up, eventually the rate of change of the rate of change of the rate of change is going to zero out. Unless you have a spring. If you have a spring, then you can always continue taking a derivative. That's why you can take derivative of a sine forever. What's a 100th derivative of a sine? Because it's always going up and down, up and down, up and down. Does that make sense? But if you take a polynomial, eventually you take more derivatives. The more derivatives you take, it will eventually zero out. Cool, right?